do with decimal names for real numbers, all right? And let's look at an example or two and see if this one generates something. Oh, suppose, for example, we were to look at a number such as 5/4, which you and I have been calling a rational number, certainly. And if we were to write a decimal equivalent for this number, we know that it's equal to, and anyone, Doug?
1.25.
What we say is 1.25. And notice now that the decimal stops. It actually terminates. And we refer to this as a terminating decimal. Now, suppose we were to have another rational number such as 1/7. And I don't think it's quite as obvious what the decimal equivalent of this number is. And one way to find it, of course, is to simply do some long division. Let's actually perform this division and see what happens. 1, 2, 3, 4, 5, 6 zeros. Let me include those zeros. Now, 7 into 10, of course, goes what? 1. Let's perform this long division process. The remainder of 3. 7 into 30 goes what? 4. That's what? 28 with a remainder of 2. 7 into 20 goes 2. That's 14 with a remainder of 6. Is that right? 7 into 60 goes 8. That's what? 56 with a remainder of 4. 7 into 40 goes 5. And that's 35 with a remainder of 5. Now, 7 into 50 goes 7. And that's 49 with a remainder of 1. Is that right? Now, notice at this point, what we're going to do is to repeat the long division process as we have right here at the beginning. Is that right? Because it's now going to be 7 into 10, and that's going to be the number 1. And in fact, that 1 is now going to begin this cycle of repetition as we see it right here. And let's indicate this by 0.142857. And let's put a bar over this entire number to indicate that it is one of these repetitive numbers. And in fact, we refer to this as what? As a repeating decimal. Isn't that right? Now notice in this case that we have a rational number, and if a number is rational, then its decimal equivalent is going to be what kind of a number? In this case, it's going to be either what we call a terminating decimal, or in this case, a repeating decimal. Is that right? So a rational number can either be a terminating decimal equivalent, or else it may be a repeating decimal. Is that right? Now, notice that the converse of this statement is also true. And let's indicate that. Well, let me call this one number 1 over here. And let's refer to a second example. Suppose we were to take a number, such as 3.5. And here now is a decimal equivalent. And what I'd like to do is to write a rational equivalent for this number, 3.5. And of course it is what? We may think of this as, this is simply 7/2. And there's no problem in deciding what that rational equivalent of 3.5 is. Suppose I were to take a number such as 1.27 bar, which indicates a repeating decimal, 27, 27, 27 on forever. And what we'd like to do is to write its rational equivalent. And perhaps the job here is a little bit more difficult, but I think it's one that we are familiar with. Let me rewrite this as 1 plus, and then this is 27 100ths plus, and then it's 27 over 100, what? We may think of this as 100 squared plus 27 over 100 cubed. And I think now you see the pattern, and these 3 dots indicate that it goes on forever. If we now were to look at that and factor out in the numerator that number 27 in each case, notice you have 1 100th plus 1 100th squared plus 1 100th cubed, and so on forever. Now, looking at what's inside parentheses there, what kind of a series do you see there? What kind of a series is that? It certainly is an infinite series, and it is a special kind, Bill?
A geometric series.
A geometric infinite series in which the number r is going to be what number? It's going to be what? 1 100th, which is certainly an absolute value less than 1. So what then can we say? What is going to happen to this infinite series? But it is going to have a limit. And if you remember what our formula was, it's going to be what? A sub 1 divided by 1 minus what? 1 minus r. So a sub 1 in this case is 1 100th divided by 1 minus, and the number r is also what? 1 100th. Okay? Now let's see what this is then going to give us. That's 1 plus 27 times. Well, of course, this is 1 100th 1 minus 1/100th is what? 99 100ths. And 1 100th divided by 99 100ths is what?
1/100.
This is 1 99ths. And now there we have 1 plus, that's 27 over 99. 9 will divide both 27 and 99, and we have 1 plus what? 3 11ths, and 1 plus 3 11ths has a simpler name of what? 14 11ths, and there then is its rational equivalent. All right? Now notice what we have in this case, an example under idea 2 here. Here we have a terminating decimal, and it may be written as a rational number, in this case of 7/2. And here we have a repeating decimal, and it too may be written as a rational number as 14 11ths. So what then is our conclusion? But that if we have what? A terminating decimal, or a repeating decimal, in each case it may be written as what? As a rational number. Very good, as a rational number. Now, notice everything that we have said here refers specifically to rational numbers, is that right? Let's call this our heading of rational numbers, and perhaps we can now say something about irrational numbers. So let me call this idea B, in which we have here some discussion about irrational numbers. Well, let's see now. Let's look at an example. Suppose we were to take the number the square root of 2, which I think we've all agreed is an irrational number. And let's see, we may say this is equal to, and if you remember an approximation, or in fact 1.41421, I believe, and so on forever. All right, is a name for the number square root of 2. And let's see now, pi is one of these irrational numbers, and does anybody happen to remember an equivalent name for pi? 3.14159. I remember it out to that number of places and some dots. Now notice in each case here, the number certainly does not terminate. It does not end. And in fact, from what you've seen here, and computers have taken these numbers out to, in fact, the number pi out to 1,000,000 places, believe it or not, and it has shown that there is no repetition, and there is no repeating aspects to this number whatsoever. So what then can we say about an irrational number? And the decimal equivalent, if the number is irrational, its decimal equivalent is going to be what kind of a number? It can be what? It will be what? Non-terminating, if we were to use that phrase, a non-terminating decimal numeral, or in fact it may be what? And it is also what? Non-repeating, a non-repeating decimal numeral, okay? And in fact, the converse of this statement is also true. Let's look at it, and let's come up here. Suppose, for example, well, let me make up some number, such as 5 point, let me just try to establish some pattern, 112, 113, 114, 115, 116, and I think you see the pattern that I'm establishing. Let me indicate some dots to say that this goes on forever. Notice there is, it certainly does not stop, and there is no repetitive aspect to this, and so you conclude that this is what kind of a number? That the number is written here, this decimal equivalent, Steve, is?
Well, it's non-terminating, it's irrational.
It's an irrational number. Here we have started out with what? A non-terminating, and also what? Repeating decimal numeral, and our conclusion is that in fact this number is what kind of a number? An irrational number, all right? An irrational number. It's quite easy to generate these irrational numbers. Just start out with any old number and establish any kind of a pattern that you want, and constantly change that pattern and indicate the 3 dots that it goes on forever, and that then it will certainly not repeat, and it does not stop, and that makes it an irrational number. Okay? Well, let's see now. Let's go on and look at another idea which is somewhat connected to this one. And well, let's see how this might go. Let's take one of these numbers as I have there. 5.112, 113, and so on, indicating that it goes on forever. We have this irrational number. Let me take another irrational number, such as 5.112, 115, and so on forever. All right? Now, I think you'll agree that we have these 2 irrational numbers. Now, can anyone think of some number which is then going to be between these two irrational numbers. And let's see now, can you come up with some number which you can put in here, Bill?
5.112114.
5.112114, certainly. Now, if we put 3 dots on there to indicate that it goes on forever, we have made it into what kind of a number? We have made it what? Irrational. Now, we have started out with 2 irrationals, and between those 2 irrationals, there is this another irrational number. Is that right? And in fact, if we did not include the 3 dots, it would be what kind of a number? It would be rational. And if we have the 2 irrational numbers, we then have put a rational number between them. Is that right? Suppose we started out with 2 numbers that were rational. All right? Would the number 5.112114 on forever be between those 2 rational ones? Yes. And in fact, we then would have what? An irrational number between 2 rationals. And in fact, if we drop the 3 dots on that one, we would have what? A rational number between 2 rationals. So to generalize this, what can we say? What would our conclusion be? Between any 2, what? Between any 2 real numbers, there's always what? Another real number. So let's write that down. I think that's quite an important statement. Between any 2 real numbers, okay, between any 2 real numbers, there exists, or there is, another real number. All right? And this property turns out to be quite an important one, and we give it a name and call it the property of density. All right? Some people refer to the fact that our number line is dense, or our numbers are dense, using this idea right here. Well, let's see now. I think perhaps when we're dealing with irrational numbers, certainly, there are times when we want to approximate and when we want to round off. So let's say a few words about rounding some of these numbers off. Suppose we were to take this approximation as we have for, say, the square root of 2, which we wrote as what? Well, this is what, 1.41421 and so on forever. Is that right? Now, let's write this as an approximation. We'll say to the nearest thousandth, okay? And notice that we put a little dot over the equality symbol to indicate that it is an approximation. And if we were to take this out to 3 decimal places, what then would be its equivalent? And how may we say that, Steve?
1.414.
1.414. And I think this is probably the number that one sees in tables most of the time. Let's look then, say, at the number pi, which is 3.14159 and so on forever. All right, and now let's write a decimal equivalent to it, for it out, say, to the nearest thousandth. And what one then would you like to say about this one, Vic?
3.142.
3.142. And now notice in each case something different happened. In the first case, we looked then at the 4th digit, and since it was what? Less than 5, our agreement is that we then will simply drop all digits thereafter and write that approximation. And then in the other half of the rule says if the 4th digit in this case is what? 5 or more, then you add 1 number to the previous digit in your approximation, and in fact that's exactly what we have here. So let's continue using that rule. And looking at, say, that number 3.142, I think you will agree just from that rule that this is certainly greater than or equal to what? 3.14 what? 15. It's greater than or equal to this one, and it's going to be less than what number? 3.14 what? 25. And certainly the number pi, I think you will agree, is going to be between those 2 numbers right there. Okay? Well, I think that's all that we need to do in today's lesson, so let me give you your homework assignment.